Now we are thinking about Newton's third law, and you've probably heard one version of Newton's third law at some time or another. For every action, there's an equal and opposite reaction. It's much more clear and precise to say force instead of action. For every force, there exists an equal and opposite partner force. If for any force that exists, there is always a third law partner force, so to speak, that comes along with that first force. To put it another way, both the force and the partner force exist simultaneously. As long as the force exists, the partner force exists. Or you could flip that around. You could think of the partner force as the original force, and what you previously thought of as the original force is the partner force. And as long as either exists, the other must exist. These two forces in a third law pair are equal and opposite. Equal means two things, and opposite means two things. For equal, the obvious meaning of equal means that they have the two forces have the same strength, the same magnitude, the same size. Equal also means that they are almost always, maybe a few exceptions here and there, the same type of force. That's important. That's hard to get used to, but that's important. Same type of force, equal in that sense. And then opposite, again, means two things. One of them is kind of obvious. The two forces in a third law pair point in opposite directions. And the other aspect of opposite is that for one force has a source, and some other object that feels receives the force. But for the partner force, those roles are flipped around. Here's one way of writing two forces in a third law pair. One force is a force from thing one on thing two, and it'll always be the case that its partner force is a reaction, so to speak, by two. A force from two acting back on thing one. The source of one force is the thing that receives the partner force, and the thing that received the first force becomes the source of the partner force. Let's go back and think about that example that I talked about when introducing the idea of a normal force. My hand pushes on the blackboard, and then the blackboard pushes back on me in the opposite direction. That force from the blackboard pushing on me was our first example of a normal force. A vertical surface pushing in the perpendicular direction, that's a normal force. The vertical blackboard pushing horizontally on my hand. But of course, my hand is also a vertical surface pushing horizontally on the blackboard, so the force from my hand on the blackboard is a normal force. The force from the blackboard on my hand is a normal force. Those two forces are an example of a third law pair. Let me just draw that out. There's the blackboard. And there's my hand. And then there's a normal force from my hand on the blackboard, pushing the blackboard that way. Normal force from hand on blackboard. And when we're thinking about the third law and third law partner forces, it's always a good idea to write these subscripts to identify where the force is coming from and what the source is acting on. So there was a force from me pushing on the blackboard, and then there was a force from the blackboard pushing in the opposite direction on me. normal force from the blackboard on me. And those two forces were a third law pair, action and reaction, third law partner forces. They are third law partner forces in the sense that they are both the same type of force, as you'll always see in a third law pair of forces, and they are equally strong because if I push harder, that is, if I increase this force, I feel more resistance from the blackboard. Feeling more resistance from the blackboard means this force gets stronger. My push gets stronger, and the push back on me gets stronger because these two forces always have equal strength. And then, of course, opposite. Obviously, the two forces point in opposite directions. And for those two forces, the roles of source and receiver are flipped around. In this force, the hand is the source, and in this force, the hand is receiving, feeling the force from the blackboard. In this force, blackboard feels the force, blackboard receives the force, and it becomes the source of the other force. That's the pattern for a third law pair. That's always the pattern for a third law pair. Every third law pair shows that pattern, and the trick is to be able to recognize that pattern when it's there in a particular situation. That's easier said than done. It takes a little practice, takes a little time to get used to it. But let's look at a couple of examples. First, imagine I'm pushing a couple of crates across the floor. So here's crate A, and here's crate B, and here I am pushing. And the crates are moving, and I'm moving all to the right. And to keep things simple, we'll say that everything is moving with a constant velocity. Constant velocity means no change in velocity. The rate of change in velocity is zero, so the acceleration is zero. There is no change in the velocity. So that implies the acceleration, which is just change in velocity divided by the length of time when you are watching for that change, is zero. Zero acceleration. Okay. Now, let's think about the forces on me, the forces on crate A, and the forces on crate B. And let's do this systematically in the form of free body diagrams. A free body diagram showing all the forces on me, a free body diagram showing all the forces on A, and a free body diagram showing all the forces on crate B. And we'll include all the details that you need to have, all the details that you want to have in a good, complete free body diagram. First, forces on me. In a free body diagram, again, we're using the simple model of the point mass model, where we're not interested in the different parts of the moving thing, namely me. We're just thinking of that moving thing, namely me, as a point-like lump of mass moving at a constant velocity to the right. And free in free body diagram means we keep the graph as simple as possible by not drawing in any of the other things that are in contact with or interacting with the object in question, namely me. The only things that we draw are a dot to indicate me, and then arrows to indicate forces, and then some more arrows to indicate a coordinate system. So what are the forces on me? There's the weight, the gravitational force from the Earth on me, gravitational force from Earth on me, and then of course I'm not falling, so that means there must be an upward force that cancels out this force, and that would be a normal force from the horizontal floor pushing vertically on me. Normal force from the floor on me. And I'm pushing on crate A, but as I push on crate A, I feel some resistance from crate A. Just as when I pushed on the blackboard, I felt some resistance the other way from the blackboard. That resistance from the blackboard was a normal force from the blackboard, and similarly, as I push on A and feel resistance, that resistance is a normal force from crate A on me, specifically a normal force from this vertical side of crate A, pushing backwards on me, resisting my push. And then there's one more force, very important force. Whenever I take a step forward, whenever I push off on my back foot in order to move forward, my back foot stays stuck to the floor. My back foot does not slip backwards as I try to move forward. My back foot is not slipping. In a situation where there could be slipping but there isn't, slipping is prevented. Slipping is prevented by static friction. So there's a static friction force from the floor on me. And the slipping, if my foot did slip, I try to move forward and the foot slips backwards, the slipping would be that way. But since slipping that way is being prevented, the static friction force must point opposite to the slipping that is being prevented in order to counteract, to fight against the slipping. So that static friction force from the floor on me specifically the floor on the soles of my shoes, is a forward force. And of course, since I'm not accelerating, Newton's second law tells me that if there's no acceleration, there's no net force on me. So in order to have no net force on me, there had to be a rightward force here to cancel out the leftward force. And so to make the net force along this direction 0, just as this force cancels out the weight force to make the net force along the vertical direction also 0. So in this case, 0 net force. And in a free body diagram, we also want to say what the net force is like. If there is a net force, you draw an arrow showing the direction of that net force. And if there's no net force, you just write net force equals 0. Finally, one other thing that you want to have in a free body diagram is a coordinate system. Why you want a coordinate system becomes more clear when we get into more complicated situations, more complicated analysis later on. When we do that, it's helpful to have a coordinate system. It's helpful to know what the positive direction is and what the negative direction is. So as far as the movement is concerned, horizontal to the right we'll call the positive direction because we usually like to put the direction of motion in the positive direction of our coordinate system. There are also vertical forces in this case, so we might want to have a coordinate system, have a vertical coordinate system to know which way is positive vertically and which way is negative vertically, and so we'll just choose up as the positive vertical direction, down as the negative vertical direction. So that's a complete free body diagram for all the forces on me. Now, a free body diagram for crate A. There's our dot that'll represent crate A, and one force on crate A is, of course, the weight, the gravitational force from the Earth on crate A. And then, just as I was not falling, even though I felt a downward pull from gravity, crate A is not falling, even though it feels a downward pull from gravity, so that's a sign that there's an upward force on crate A, and that upward force would come from the surface below crate A pushing up on crate A with a normal force. Normal force from the floor on A. And then, of course, I'm pushing forward on crate A. There's a normal force from the vertical surface of my hands pushing perpendicularly, pushing horizontally on A. Normal force from me on, or normal force from my hands on crate A. But just as I was pushing on crate A and felt some backwards resistance from crate A as I pushed, crate A is of course pushing on B, and B resists that push. So as A pushes on B, A feels some resistance because B is pushing back on A. In other words, there's a normal force from B on A. This vertical surface of B pushes horizontally to the left on A. And then, of course, since the crate A is sliding forward, there's probably some sliding friction, some kinetic friction from the floor on the bottom surface of crate A. Kinetic friction always points opposite to the velocity. So A's velocity is to the right, so there's a kinetic friction force to the left from the floor on crate A. And then finally, a free body diagram for all the forces on crate B. It's another crate being pushed forward, so all the free body diagram for B would look similar to the free body diagram for A. Just for completeness here, again, we note that the net force on A is 0. We know that because A is not accelerating. And the coordinate system that we would set up for A would just be the same as the coordinate system we had set up for me. Finally, for B, all the forces on B start with a gravitational force from the Earth pulling down on B, and then just like it was for me and for crate A, there's a normal force from the floor pushing up on B, and then A was pushing B forward. The vertical surface of A that was in contact with B is providing a horizontal push on B. Vertical surface pushing perpendicularly, horizontally, that's a normal force. Normal force from A on B. And then B is sliding across the floor, so there's kinetic friction on B. The kinetic friction points opposite to B's velocity. B's velocity is this way, so the kinetic friction points to the left. Kinetic friction from the floor on B. So those are all the forces on me, all the forces on crate A, all the forces on crate B. Just for completeness, remember that crate B has zero acceleration, its velocity is constant, and Newton's second law tells us that if acceleration is zero, then there's no net force, because it's net force that causes acceleration. If there were a net force, there would be acceleration. But there's no acceleration, so that means there must be no net force. There we are. And among all those forces, there are some third law pairs. Every one of these forces has a third law partner force, but only some of these forces have their third law partner drawn into this diagram. So where are the third law pairs in this diagram? Which third law pairs have both elements of the pair somewhere in this diagram? Well, here's one third law pair. There's a force from crate A on me, and then from crate A on my hands, and then there's a force from my hands on crate A. So I'll connect them like that. That's a third law pair. We know that they're a third law pair because they are the same type of force. Both forces in a third law pair are the same type of force, and they're pointing in opposite directions. This force points to the right, this force points to the left, and for one of these forces, A is the source, and for the other force, A is the thing that receives a force. And for one of these forces, my hands receive or feel a force, but the receiver of one force then becomes the source of the other force. Comparing this force to this force, the roles of source and receiver are flipped around. That's what a third law pair looks like. And there's one other third law pair in here. There's a normal force from A pushing on B, and then there's a normal force from B pushing the other way on A. We can tell they're a third law pair because they have all the characteristics of a third law pair. They are the same type of force. They're both a normal force. They're pointing in opposite directions, just as a third law pair of forces should. And again, the source of one force is the receiver of the other force. And the receiver of this force is the source of the other force. The roles of source and receiver are flipped around when you go from one force to its partner force. So those are the only two third law pairs in all these diagrams. Don't be misled into thinking that just because, let's say here there's a leftward force and here there's a force in the opposite direction, those two must be a third law pair. No. They're not a third law pair, and you know they're not a third law pair because they're not the same type of force. And you also know they're not a third law pair because both this force and this force are acting on the same thing. They're both acting on me. They're both acting on my hands. Whereas in a real third law pair, the two forces act on two different things. Here's a force on B, and the third law partner of that is a force on A. And then in this third law pair, here's a force on my hands, and the third law partner is a force on something else, crate A. Right. The third law, to put it another way, the third law always describes an interaction between two things. And those two forces in a third law pair, each of those two forces acts on one of the two interacting things. So in an interaction between crate A and crate B, for that third law pair of forces, one force would have to act on B and the other force would have to act on A. And in an interaction between my hands and crate A, the third law pair associated with that interaction would have one force acting on me, acting on my hands, and the other force acting on the other interacting thing, crate A. Like I said, it takes a little bit to get used to. You'll have plenty of opportunities in class to practice getting used to this. Just one more thing to finish up here. Let's look at one more example of a force and its third law partner. Imagine a rock falling through the air, and there are just two forces acting on that rock. There is, of course, weight, the gravitational force from the Earth on the rock. And then if this rock is traveling at a sufficiently high speed, there'll be a drag force on the rock. Drag force always points opposite to the velocity. The rock is falling, the velocity is down, so the drag force would have to point up. Now, what is the third law partner force of that weight force? So the third law, so the force here that we're dealing with is the weight force, gravitational force from the Earth on the rock, gravitational force from the Earth on the rock. The two forces in a third law pair are the same type of force, so the partner force to this must also be a gravitational force. The partner force of this force is not that force. Can't be, because they're different types of force. This force was a force pulling down. The partner force is opposite. Two forces in a third law pair are opposite. So this is a gravitational force that's pulling up. And in a third law pair, the receiver of one force, the rock, becomes the source of the other force. And the source of one force becomes the thing that receives, the thing that feels the other force. For the two forces in the third law pair, the roles of source and receiver are flipped around. So, in other words, they are a third law pair, which means this force and this force are, strange as it may seem, equally strong, because that's the way third law pairs work. These two forces have all the characteristics of a third law pair, so they must be a third law pair. And if they are a third law pair, they are equally strong, even though it doesn't seem that way, because you see very clearly the effect of the force on the rock. You see the rock accelerate. You don't see the effect of this force on the Earth. You don't notice the Earth accelerating up this way because it's feeling this gravitational force from the rock, even though it really is feeling this gravitational force from the rock. The magnitude of the gravitational force from the Earth on the rock is just as equally strong as the gravitational force from the rock on the Earth. So to simplify things, I'll just call this amount of force plain old F. And both rock and Earth feel, imagine a situation where the rock and the Earth both feel a net force of F. Now let's apply Newton's second law. The acceleration of the rock is just the force that the rock feels, F, this much force, divided by the mass of the rock. And the acceleration that the Earth feels is the same amount of force, right, this much force, divided by the mass of the Earth. Well, we've got an inverse proportionality here, because in both of these cases, this number here is the same. So we have an inverse proportionality between acceleration and mass. In inverse proportionality, whenever one variable gets larger, the other variable gets smaller. This denominator here is much, much bigger than this denominator. This denominator is much, much bigger than this denominator. The numerators are equal. So this fraction is much, much smaller than this fraction, which means this acceleration is much, much smaller than this acceleration. Mass of the Earth, much, much bigger than mass of the rock. That implies that the magnitude of the Earth's acceleration is much, much less than the magnitude of the rock's acceleration. In other words, this much bigger acceleration is easy to see. This acceleration is so extremely tiny that we don't notice it. It's there, but it's too small to really matter very much. So in other words, according to the third law, the rock and the Earth, when they interact gravitationally, are both feeling the same amount of gravitational force, but the effect of that same amount of force is very different on the rock and the Earth, because the rock and the Earth have different masses, different amounts of inertia. The Earth has much, much more inertia, so it's much, much more difficult to accelerate. Its acceleration is too small to notice.